not sure ages, and also if you want to do a starting point, because sometimes you get confused about where you're starting at, I will use one of these positions right here, either the one with the 2 methyl groups or the one with the 2 bromo groups. Probably the one with the 2 bromo groups. Start with being like number 1, so you know how to circle around and make it 8. And you want to at least count how far and make sure you count it properly. So we got 8, prefix for 8. What type bonds? Single, double, or triple? Single. A, octane. But since octane is a straight chain molecule, not cyclic. How to indicate a straight chain molecule from being a cyclic molecule? We must add the word cyclo. Anytime you got a ring, you gotta have the word cyclo. Next, we want to box the group that's attached to the molecule. We'll box, 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 and box. We're going to name our groups inside the box. This is methyl, methyl, ethyl. Now for the halides. Now try to throw the halide stuff in there. But also when we did kind of briefly mention about the halides on the chemical model lab that we ended up doing on Wednesday. Now for the halogen, for bromine, chlorine, fluorine, iodine. If this thing was not attached, what's the name given to Cl for the periodic table? Chlorine. For the halides, it's their constituents. You'll drop the INE and add an O. So that will make it chloro. This other molecule, according to the periodic table, what's the name of Br? Bromine. Similar to how we did chlorine. You drop the INE and add an O. So that'll be bromo, bromo, and chloro. Now the question comes to how do you number this molecule? Notice we said we're going to start off with the carbon atom with 2 groups and call that carbon number 1, right? But there's 2 carbon atoms with two groups attached to it. How do you know which one to start with? We're going to actually have to start with each one. We randomly start with the one with the 2 bromine groups and call that carbon number 1, and then we're going to do the one with 2 methyl groups and call that carbon number 1. Randomly, because remember there's no set, because both got 2 of the same groups, right? We don't know, do we use the Br group first, or do we use the methyl one? What's going to let us know which one actually is carbon number 1? We're going to have to do our lowest number count. Remember how we did the lowest number count group? If there was only one group that had 1 carbon atom group, it's already easy that we knew exactly where to start at. Here it's not saying we're going to start. We don't have to do. We only got 2 places to start from. This one or that one. You don't have to randomly go ahead and then pick all of the individual places. Yes.
Is it possible to use the logic of if you have a branch that has 2 off of a substituent, look at the very nearest substituent and just start there? Because if you look at bromide, you know, bromide has a C in between, or carbon in between the next substituent. But this one at the top doesn't have any.
Again, like what it does, you're calling it different, but all you're doing is the lowest number combination.
So, but wouldn't that be the lowest combination?
Yes, you come with the lowest number combination. Because you just say the same thing, all the big will try to walk you through what you just said.
Okay, right.
Now, sometimes you go ahead and eyeball and look at it, or sometimes basically you go through the step, you're going to get tricked about sometimes. Because sometimes you look at one thing, you're like, I didn't really see that one. Just like I said, when you're going through some kind of intersection, like, I didn't see the car coming. That's why I said to take your time and do the process. After a while, when you start getting more comfortable with it, you can probably maybe skip some of those individual steps. For the name of this molecule, there's only two places I can either start with. I would either start with the BR group or I can start with the methyl group. What I'm going to do randomly, I'm going to start with the BR. Equally, like someone could randomly start with the methyl group, just at least have a starting point. If I had the BR, if I do BR, I will have a 1-1 combination. From the BR, if I go clockwise, if this is 1, 2, 3, 4, 5, 6, 7, I will have a group on 8, hold to my 8. I will have something attached to carbon number 1, another group attached to carbon number 1. I will have a branch attached to carbon number 4, and another one attached to carbon number 4. I will have a branch attached to 5, and I have a branch attached to 7. BR2, clockwise. Remember, every time I do clockwise, equally I could have also done counterclockwise. Remember, the rule does not state you have to go in one direction, you have to do both directions. Yes?
How will we start counterclockwise? Just
When we go clockwise, how the clock goes. So we're just going from left to right, that's where the clock goes. And you do like that. 9, 10, 11, 12, all the way across here for the clock. For counterclockwise, my notes will be 1, 1, 3, 5, 6. Counterclockwise, my note will be 1, 1, 3, 5, 6, 6. Everybody see I got my counterclockwise note. Of my counterclockwise numbers, which number is the lowest number combination? 1, 1, 3, 5, 6, 6. Counterclockwise. This represents the champion for the BR group arrangement. If I use the BR2 groups. But equally, I could have used the 2 methyl groups. So now I have to count based upon doing the 2 methyl groups. For the 2 methyl groups, which is methyl 2. If I go clockwise, this is number 1. Let me just put number 1 first. This is 1, 2, 3, 4, 5, 6, 7, 8. Clockwise, the number is going to be a 1, 1, 2, 4, 6, 6. If I do counterclockwise, still using B into my 2 methyl groups as my starting point. 1, 2, 3, 4, 5, 6, 7, 8. It's a circle one. Counterclockwise, my notes will be 1, 1, 4, 4, 6, 8. Now for the methyl group, which one is my lowest number combination? Lowest number combination is 1, 1, 2, 4, 6, 6. This is my champion to represent the methyl group. That's the lowest combination for the methyl group, for the two methyl groups. This is my lowest combination for my two BR groups. Now I gotta compare between those two, between these two numbers, which one is the lowest?
The methyl.
The methyl. So we actually start with the methyl group, have the numbers of 1,1-dimethyl, 2-ethyl, 4-chloro, 6,6-dibromo. That's 1-methyl, 1-methyl, 2-ethyl, 4-chloro, 6-bromo, and 6-bromo. Now, let's say on the exam, you're not going to have a whole bunch of those particular ones because they'll take a little bit more time as far as doing those. But you may have one of those like on a homework type one. And again, a lot of times it's not like, sometimes you can eyeball, because basically when you do it, there's two choices anyway. You got a 50-50 choice anyway. From the 50-50 choice, I can either start with the bromine group or I can start with the methyl group. So at least you got a 50-50 which way to start. From each one of them, you either go clockwise or counterclockwise. So you basically got 1 in 4 chance of getting the answer right just by randomly picking one. You may luck up and pick the right one being the bromine group or the right one being the methyl group. So if you go through the whole process, you can see why it's the methyl group that actually wins out compared to the BR group that wins out. The in 2C3 groups, even though both the carbon atoms and the halides are exactly equal as far as the priority as far as the directions. Now I do want to point out, this video is kind of more the ones that would be a challenging one. I'm not going to go ahead and start out giving you all those little crazy type ones and stuff on those. But I do want to give you one in which case, for example, it's a little bit more challenging. How would you go about actually determining which direction to go in? Again, like I said, if you can figure this particular part here out, you're going to get all those ones down as far as X exam number 1. So as far as naming this molecule, it would be dibromo being first. So it would be 6,6-dibromo, 4-chloro, 2-ethyl, 1,1-dimethyl, cyclooctane. 1, 2, 3, 4, 5, 6, 6 groups. 1, 2, 3, 4, 5, 6. Well, isn't that a mouthful to go ahead and say out? Now, similar how we end up doing for the straight chain molecule. Once we took the structure and came with the name, we also did what? We reversed it. We're going to do the same reversing process for cyclooctane. When we're going to draw cyclooctane from the name, how we're going to start it? Start at the back. We're going to start with, basically, octane further, we should put the word cyclo. Octane lets you know you're going to have 8 carbon atoms that will be in a ring. One, 2, 3, 4, 5, 6, 7, 8. 8 is going to be a stop sign. So basically, going to list it with a stop sign. Now, since we're actually drawing it, where are we going to put carbon number 1? We can start any place you want with carbon number 1. Now, so we said one of the cool things about like when you draw it yourself, you determine where number 1 is at. You don't have to keep guessing about if it's left, right, or center type thing and stuff on those, because you're defining where carbon number 1 is at. I generally like using carbon number 1 somewhere near the top. But you can put carbon number 1 any place you want. So in this case here, I'm gonna put on, I'll do my numbers. Let's be calling this carbon number 1, 2, 3, 4, 5, 6, 7, 8. Again, so I'll do my numbers. I don't have to go and do it directly as far as number order. I can do a carbon number 6, I got a bromine. And on carbon number 6, I got a bromine. Carbon number 4, I have a chlorine, a chloro. Carbon number 2, I have an ethyl. And on carbon number 1, which I already defined what my carbon number 1 would be, I have a methyl. And also on carbon number 1, I have a methyl. Like I said, you have to put the carbon number 1 any place you want it to. Let's begin to put it some other place. I want carbon number 1 to be at the bottom. I want to do something different. 2. There's 1, 2, 3, 4, 5, 6, 7, 8. You can put on carbon number 6 a Br, carbon number 6 a Br, carbon number 4 we have a Cl, carbon number 2 we have 2 carbon atoms, and carbon number 1 we have a carbon and a carbon. Because you want to start it's a little different. And you may go ahead and peep on somebody else's paper. Oh snap, brings it out. Your molecule and their molecule are the exact same. If you take this molecule and then going to rotate it, take a sheet of paper moving, you'll see that these two structures are the exact same. It looks different because we're like far like where your starting point, far where your the initial starting point type thing and stuff on the molecule. Because you start with a different starting point, it looks like they're two different molecules. But because you actually rotate, take a sheet of paper and actually move it and line them up, you'll see that both molecules are the exact same molecule. Isn't that fun? Oh, you know what it's always the devil's in the details. Because actually when we finish particular part naming the molecules, we're going to come out as far as like developing different structures with the same molecular formulas. Have we ever done anything for what basically have like in which we had an atom from Chem in which the molecule the atom or the molecule could have been the same but have different attachments? Or you may have like, for example, in Chem, an atom with the same atomic number but different atomic masses. Yeah.
Are you going to have questions like that in the test where we have to try to figure out whether two molecules are the same?
No, because it's not a study guide. No, it's not a study guide. I'm not trying to go off the very end and just go in there. We'll put it in for you. Now, I'll be consistent from the study guide one. If it's not a study guide, it's not fair game. If it's on the study guide, then it's fair game. But we didn't do a comparison between the two as far as that molecule. But we did kind of mention about drawing different molecules with the same molecular formulas. How are we feeling as far as taking the name of a cyclic molecule and coming up with the structure? And hopefully those should be not too hard as far as doing those. The main thing to remember as far as doing that molecule is you got to start from the back. Start from the back, do your numbers. Now when you're drawing a molecule, you can number it any way you want to. You determine the numbering factor. Now when someone else number it, you got to then go by their numbering order. But when you draw it, you make your own numbering order. So somebody else who brought it, if I want to come name it, I got to follow your order. When I draw, you got to follow my order. Drawing of different molecules with the same molecular form. cool things about carbon atoms. For example, you get like a, if this was a G-Chem, I get NaCl, and there's only one molecule of NaCl. But for example, I got like a formula of C6H12. There's a whole bunch of molecules with the formula C6H12. And you're probably saying, what are you talking about? Now, also I would say for the name of the molecule, the formula C6H12, all of them have the same molecular forms, they have something to say about themselves. But you're going to have different atom connections. When you got something to be the same, you can use the word iso. We're talking about drawing different isomers. Drawing of different isomers. I'm trying to go to structure isomers, constitutional isomers. I need to make sure before I get the name for the structural constitutional isomers. So one is that you have to get like there's a geometric isomers, there's a constitutional isomer. But I'll check the names before. Let's for example, I got a molecule C6H12, and I want to come up with a bunch of different molecules with the same formula C6H12. But we're not going to randomly jump around and stuff here like a chick with a head cut off and just jumping around. We have a pattern to how to do this thing. The first thing we do with our pattern, we're going to come with 6 carbon atoms in a straight line. This is like having 6 carbon atoms, 0 branches. No more branches. What name is given to a molecule with 6 carbon atoms in a straight line? Hexane. Now for a pattern, we start with 6 and 0. What another way to get the number 6? Step down 1. Another way to get 6. 5 and 1. See, you were trying to going up here. Come back here. So you can do 5 and 1. 5 means we're going to put 5 carbons in a straight line. You're going to have one carbon atom be somewhere in the middle of the molecule. 1, 2, 3, 4, 5. Now I got one more carbon atom I have to attach it somewhere in the middle. You have to attach it to either carbon number 2, 3, or 4. What if I attach it to carbon number 1? What's my longest carbon chain? 6. Even though it looks kind of weird and stuff here, because all I'm going to do is basically I can go up and then go over, and then I change particular one. So once I basically get up, I can immediately going over, and I still have 6 carbons in a straight line. If you put it on carbon number 1 or carbon 1 of the carbons at the end, you'll get back to your longest carbon chain. So your branch got to be somewhere in one of those middle carbon atoms. There are 3 middle carbon atoms to use. What I like to do is have a process. I start with the first one. The first middle one was carbon number 2. Is this molecule different than the molecule made earlier? Yes, that's a different molecule with the same molecular formula. We also can do another 5 and 1. Again, can I do like a little experiment 1? We're going to change, we're going to keep something consistent, we're going to change one verb at a time. What we're going to keep consistent, we're going to keep our number of carbon atoms the same. 1, 2, 3, 4, 5. Remember we had 3 places to actually put that one carbon atom. We could have put it on carbon number 2, carbon number 3, or carbon number 4. But we can't put them all 3 carbon at the exact same time, so we can do one at a time. So next I put it on carbon number 2. Next I'm going to redraw my skeleton structure, and this time I'm going to put it on carbon number 3. Now we're going to compare carbon number, molecule 1, molecule 2, and molecule 3. Are those different molecules? Yes. Now I'm gonna do my next little set, which I go 5, 1, and I'll keep my carbon skeleton being the same. And this time I'll put my group on carbon number 4. Now, if I put on carbon number 4, is that different than the molecule made earlier? How would you name this molecule?
The same way you named the molecule.
But you made it 2-methyl pentane. How would you name this final molecule?
Same way.
2-methyl pentane. Even though now it may look like kind of different, but all this molecule is took it and just flipped it over. It's like, I'm going to say this textbook right here. And then I'm going to say, look over there. And I flip it over around like this right here and say, that'll be another $300. They're like, what are you talking about? Yeah, I just sold you two different textbooks. Because the first one textbook over there had the thing like this right here. The second textbook, when you look over there again, kind of down this way. Give me 2 different sets of money for it. You look at a person like, you must have lost your mind. All it's really doing for here also is just they took the same molecule and just flipped it over. And you're like, I'm not getting fooled by the because of the fact you flipped it over. Again, another way of actually saying you got a different molecule now. If you got 2 different molecules, if you can name them, if you got the 2 of the same name, they're the same molecule. So as far as a different molecule, you're done with 2, with 4, 5, and 1. Can we step down even further? We can also do what? Come up with 6. 4 and 2. So let's try 4 and 2. 4 and 2, we got 1, 2, 3, 4. Now here's the interesting part about the 4 and 2 one. We actually have a couple options. We can actually put those 2 carbon atoms together in one unit to make a total of 2. Or we can make those 2 carbon atoms 2 separate groups. Probably easy to make the 2 separate groups first. Which means, and now when I have 2 1 carbon atom units. If I have 2 1 carbon atom units, how can I add those 2 1 carbon atom units to my 2 other carbon atoms? Am I going to add both to the same carbon atoms, or I can split them up? If I add both to the same carbon atom, I'm going to add both to carbon number 2, 1, 2. Is that a different molecule we came up with already?
Yes.
Yes. Now notice I put it arbitrarily put it on carbon number 2. Equally, I could have put it on what? Carbon number 3. If you join, it's the same thing, but what you see is the same thing. If I do 4 and 2, keep my same carbon skeleton structure, and I went and put it both on carbon number 3 instead of carbon number 2. Would the new molecule I made be the same or different than we came up with?
Same as one before.
It still be the same molecule. But I just want you to end up seeing it so like someone like me trying to put a fast over you think I'm fooling you. Now also remember my arrangement, there were 2 things we were doing. Notice we actually put, we had 2 1 and 1s, right? We actually could put both together in the same carbon atom, or we could have split them up and put 1 on 1 carbon atom and another on the other carbon atom. So we're going to take the same one, this time we're going to split them up. Put 1 here and 1 there. It's still a branch of 2 groups, but I got my 2 groups of 2 different carbon atoms. Is this molecule different than the ones we made earlier?
Yes.
Yes. Only compared to based to another 4 carbon atom unit. And basically, it's not the same as the other 4 carbon atom unit we actually made. But then there was also a 3rd option. When we did our 2 carbon atom group, we could also put both together. And we're going to put those two carbon atom units together to form a ethyl unit. We got two carbon atom units together added to either carbon number 2 or carbon number 3. If I add it to carbon number 2, is that molecule different than what we made earlier?
Yes.
Yes or no? I got someone saying yes, someone says no.
Yes, sir.
Yes, it's different.
So it's different?
Mm-hmm.
Let me see, what's different?
Because that was ethyl.
Different.
What was 2-dimethyl?
We have the same.
2,2-dimethyl butane.
How many people say it's different? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10,
This one is 2 ethyl.
11, 12, 13, 14, 15. 15 say it's different. How many say it's the same? It's one we already made earlier. Well, how you can vote there? You say it's different. You can say it's the same, and then you will. Do you say the same or different?
I said the same, but I said different the first time, but it's not.
So it's the same? So you vote for the same then? Okay, I'm trying to. I'm like, you can at least vote for it. I don't answer. How do you say the same then?
It's not.
One. They say the same.
I did, but it's not.
Which one you vote for then? So you vote for different. Who vote for the same? Got one. One person said the same. Now, 15 people right, or one is 15. Is 50 people right and one wrong, or there's 15 wrong and one right? You try to jump in. So at least you won't leave you by yourself. It's the same.
Wow.
And you're probably saying, I don't see it, I don't see it, I don't see it. Name that molecule. Name it.
2-ethyl.
What's the name of
Heptane.
it? It's
2-ethyl.
not 2-ethyl. What's my longest carbon chain? You
Butane.
like a little zigzag some kind of food with the longest carbon chain. What's my longest carbon chain?
I got you.
My longest carbon chain is 5.
Wow.
Now when I get here, I'm obligated to go left or right. If I go right, my longest carbon chain will be 5. And I have a box on carbon number 3. That molecule will be 3-methyl pentane. We already have 3-methyl pentane. So you got the name of the molecule. Because we put the ethyl group on that chain, the ethyl group actually made the longest carbon chain still being 4 that we want it to be. It made it to a 5-carbon atom unit. And we're going to name the 5-carbon atom unit. We actually go back to what we did earlier, which is the 3-methyl pentane. Sometimes it'll act try to fool you, But I'm just saying we had one young lady, she went there and stood on the outskirts and went against everybody else. Yes.
On the test, you're not going to ask us to draw all the ice work.
No, what I'm going to ask you here, give me 1, 2, 3, 4, there's 5. I would give it, I give one like at least 6, somebody I'll probably give like there was, if there was 5 of them, give me 3. Yes.
So although they are different molecules with the same isomer.
They have the same molecular formula.
Oh, okay, okay. But
Now,
it's
basically, what they have the same, so we got the same number of carbon atoms, same number of hydrogen atoms. In fact, also the same number of bonds in the molecule. If you were to put the hydrogen atoms in the molecule, we said we got 6 carbons and, oh snap, it should be, 14. That'd be 14. That'd be C6H14. All of them should have 14 hydrogens. And you're probably how you know I'm not trying to put a fast on one yet. Let's give this molecule right here. I mean, a molecule, each one should have 14 hydrogens. So we're going to see, do we have 14 hydrogens or did I just put a fast one on you? So when we draw the hydrogen atoms on the carbon atoms, we know that carbon wants to form a total of how many bonds? 4. How many bonds are directly attached to carbon shell? 1. So I need to add how many hydrogens? 3. That's H3. I'm just going across. Look at my next carbon atom. How many bonds are shown attached to the next carbon atom? 4. I'm adding no hydrogens. Go to my next carbon atom. How many bonds shown? 2. So I need to add how many hydrogens? 2. Going to my last carbon atom. How many bonds shown?
1.
So I need to add how many hydrogens? 3. To get the total number 4. Now I go to the top of bottom, my carbon in the bottom. How many bonds are shown in test carbon?
1.
How many hydrogens do we need? 3. Going to the one at the top, how many bonds shown?
1.
How many hydrogens need to be attached? 3. Now do my count. 3, 6, 9. 9 plus 3 is 12. Plus 2, 14. All of when you do the number stuff, you should have 14 hydrogens. 1, 4. If you don't have 1, 4 and stuff, it can't be an iceberg each other. Iceberg at least have something the same about each molecule. They have the same number of carbons, same number of hydrogens, same number of bonds, different attachments. Now, like, if I were to ask you a particular one right here, I would ask you, for example, I know there's 5 of them, I would ask you, like, draw me 3. Well, we don't have to just have 6 carbon atoms, we could do a different number. I could ask you for C7H16. And I want you to then draw me 5 different molecules with the formula C6H14. I mean, not C6, C7H16. Five different. Now, how we do the 5 different? This is the 5 different one for C7H16. What we start out with? First one give me 7 in a straight line. 1, 2, 3, 4, 5, 6, 7. You can only have 1, 7, and 0. The next you would do is what? Give me 6 and 1. 1, 2, 3, 4, 5, 6. Now my 1, I have to put it in one of those middle carbon atoms. What I like to try to do is have a pattern to it. Not to be just jumping around and something like with a chick with a head cut off. I want to go ahead and start with order. Start with the first, carbon number 2, then carbon number 3, then carbon number 4 until we get the same one. So first I'll put my branch on carbon number 2. Next we'll do the same thing, I'll put the branch on carbon number 3.
It looks 7 on the top.
Is this different than the other we did so far? Yes. If I added the carbon number 4, would that be different? Is this molecule different than the one I've drawn so far? Yes or no? It's different? Not different. It's not different. If you were to name it for here, this would be hexane. It would be 3-methylhexane. We just drew 3-methylhexane just earlier. So now we cannot do any more 6 and 1. We have to now do 5 and 2. 1, 2, 3, 4, 5. Number 5 and 2, we can put both groups together if you like. 1, 1. Another 5 and 2. We can put it both on the middle carbon atom. Also, we could have done what? We can actually take them and actually split them apart. We can do 5, 1, and 1. Kept one on carbon number 2, and now put the second on carbon number 3. Or I can do 1, 2, 3, 4, 5. Put one on carbon number 1, and next one on carbon number 4. We also can have in which we can put the groups of attached to it. But then you realize how many molecules ask you to do? 5. How many have you drawn so far? 6. All I wanted was 5. You don't get any credit. You don't get any more credit for the question because you draw me more than that particular number. All I wanted was 5. Now you can go ahead and spend some more time and go ahead and draw all of the ones you want to your heart desire. It's still not going to be stuck getting more than 10 points for a particular question. That I just need was 5. Yes.
First one doesn't count.
First one counts. No, you don't have a formula. Remember, all I give you a formula. I don't give you no structure. So why wouldn't this first molecule of C7H16 count? Aren't you drawing me a structure?
I thought you said 6 different ones.
No.
No. I thought you said, how many have we done? You said 6.
This is 7 then. Right? 1, 2, 3, 4, 5, 6, 7. But all I wanted was 5. Right. But you didn't have to give me any more. Once you get 5, you can stop. You don't have to keep on going at particular numbers. When I give you a number, I'm going to make sure the molecule has more than the number I'm asking for. I'm not going to go in and exhaust it, but you get like, oh, I got to get there. What's the last one? I'm going to try to have a number which you should be able to easily get to without trying to get even super crazy about doing crazy combinations. If I got the one that has 5, I'm going to just ask you for like 3. If I know they got way more, like about 7 or 8 or something like that, I'll ask me like 5. Yes.
So if we have a case like the other one when they was both equal to the same, that's just counts as 1, or it can be.
Yeah, it's not a different, won't be a different molecule. I need 5 different ones.
So what we just did when he said they were the same, those two that were the same didn't count.
Did not count. I need a different one. I need 5 different.
So with the 6 one we did, we just need the first one. Because the other two were the same.
Look at this video, man. This video was that was fine. Second one is the one we put it up on carbon number 4. That was the one we got rid of. Carbon number 4 is the same as carbon number 3. But again, I want you to get these numbers right here. If you do the particular numbers, you actually probably get it. I would recommend as far as like if you do a branch one, start with like a 2-branch one first. They will give you more than numbers from the original one. So I would basically say if I was doing if I was trying to save time as far as doing that one, start out with 0 first, then do the ones with 2s, and then you may come back and do the one with 1s. Because the ones with 2s will give you will get a bunch of more. You know the one we did with 2s I got. From there I got 1, 2, 3, 4 ones that do the one with 2s and stuff already. And I got a lot of molecules stuff out. You get more molecules doing like a 2-branch one than probably a 1-branch one. Yes.
So that we don't have to worry about the carbon. What if the hydrogen is 16?
The hydrogen equals 16 is a single bonded molecule. Oh, we got a way of how to determine that actually should be 16 hydrogen. That there actually be 16 hydrogens on the molecule.
Like what would be? How would you make that 16?
It was 16. All would be 16. Let's go ahead and try that one. You're like, I count. How many bonds is carbon shown to have? 1. I need to add how many hydrogens? 3. This one has how many bonds shown?
2.
I need to add how many hydrogens? 2. 2. 2. 2. 2. 3. Do your count. 3, 6, 8, 10, 12, 14, And remember that's one about degree of unsaturation? Degree of unsaturation lets me know how many hydrogen atoms should be around that molecule. And we talked about degree, we've actually tried to, I'm not sure we ever get enough time to put it on an exam, but we're going to mention about the degree of unsaturation.
Now, with
Yes.
the last one, you do different?
Yes. For this molecule here, for 1 and 1, I have this molecule and that molecule. Those are the ones that split them up 1 and 1. Is this molecule the same as that molecule? The way of checking over here is to actually put a name on the molecule. That can be kind of funny when the names of the molecule too, once you draw them out, name them.
It's too much.
Jasmine is Jezebel. She's that's not really too much, because we only got an hour to figure this stuff up. But again, I get a molecule over here for drawing different structures. I will give you, like I would have it so there would be more molecules than you actually would have. I would have, for example, there was like, I know at least 7 of these molecules. So I have to actually do 5. And that way you won't have to get there and do super crazy enough to get to number 5. And also give me like a game plan about how to determine it. Now, there was one question that was asked about, for example, how do we know that 7 carbon atoms has 16 hydrogens if this carbon atom was single bonded? And the way you end up knowing about that one is by the degree of unsaturation, or what is the book called? The Index of Deficiency or something. What is it? What is it? Deficiency index or something like that, or the book had a different name for it, called like a deficiency index.
It was. I think it was like the, let me see.
You know, I'll check the title of the book, like a deficiency index or something. Degree of unsaturation. Saturation. When I mention about something being saturated or unsaturated, going back to Chem, when something considered to be saturated, when I mention about something being saturated, what does it mean about for Chem type stuff? Like for example, I got a solution of salt and water. How do you know when it's saturated? When it contains the maximum amount of solute for a given temperature. So for example, you may be also you probably heard the word about being saturated or soaked probably about before you came to college. You went out there, got the rain and stuff here, you're playing outside, and I realized about like a half a mile from home and it started pouring down rain, and you're just like dripping with water and stuff here, like you're saturated. So basically your clothes have more water than that can hold, and basically have like any excess water kind of flows off for you. When something is considered to be unsaturated, it considers less than a maximum. So when the carbon-carbon single bond is something considered to be saturated, that means these carbon atoms contain the maximum hydrogen atoms that 7 carbon atoms can contain. It cannot contain any more than 16 hydrogens. If you got a molecule of C7H17 or H18, it cannot exist. Because those 4 carbon atoms, those 7 carbon atoms cannot contain any more than 16 hydrogens, 1-6. And how we come with that number? Let's, for example, I have 1 carbon atom. What's the maximum hydrogen atom that 1 carbon atom can contain? 4. About 2 carbon atoms? We'll see in a second. Number will be 6. If I have 3 carbon atoms, what's the maximum I can hold? 3 carbon atoms.
10.
It's easy to go draw 3 carbons out of the line and then make sure everything's happy. 8. But what about ask you if I have 2,100,000,000 carbon atoms?
4 billion. 200 million plus 2.
2. Answer would be 4,200,000,000 to hydrogen. Now, you might want into it for the smaller ones and stuff. I just add them all together. Who can actually go ahead and draw out 2 billion carbon atoms? How long it take to draw 2 billion carbon atoms? Just like say, get here and try to count $2 billion by counting $1 at a time. How long did it end up taking you? Now, the reason why you get the answer for here quick is because there's a pattern to it. Degree of saturation. That's going to be C to the N, H, 2N plus 2, where N is equal to number of carbon atoms. Here's the way of checking the early ones. For N, when N equal to the number of carbon atoms. Let's, for example, I say I wanted how many hydrogen would 1 carbon atom contain. For 1, I would then plug in for N1. So I got C1, H, what's 2 times 1? 2. Plus 2, 4, so it would be CH4. 1 carbon atom, 4 hydrogens. If I had 2 carbon atoms with the maximum hydrogens, I would then put 2 times 2 is 4 plus 2, 6. That's why I get the number of big. I got 2 times 2 is 4 plus 2 is 6. So I got C2H6. And we said the number would be 6. If there were 3 carbon atoms, C3, it'll be 2 times 3 is 6 plus 2, 8. Now if the number was 2,100,000,000, 2 times that number would be 4,200,000,000, and then plus 2. So to make sure that, so we'll know that the 7 carbon atoms, the maximum hydrogen atom the 7 carbon atoms can contain is, you would do C7, H, 2 times 7, plus 2, 16.
You know, I think like, you know, when you visualize the description of what you just did, I think that plus 2 is from the chain, and those 2 heliums are just from the outside.
Yeah, basically everything from a double bond, when you actually, you end up losing them, you get a form of carbon-carbon bond. You lose them, there's not a rule about how you can end up do the count if you lose or gain them.
Yeah, that's what I'm saying. There's always going to be those 2 extra at the end because you have to join the carbons.
If you're doing for a molecule that has, that's considered to be saturated. You can't have the number to let it, because you also get the one where you can't be saturated.
So are these numbers saturated or unsaturated?
These considered to be saturated, so the degree of saturation is this formula right here. But you're probably saying, that's not as much fun as stuff for dealing with the molecule. We also talk about the degree of unsaturation. Determining the degree of unsaturation. Let's say I got a molecule of C6. Yeah, C6H6. How many degrees of unsaturation will be the molecule C6H6?
6.
Now the question is trying to figure out what is the maximum hydrogen atoms that go around 6 carbons? What's the maximum hydrogen atoms that go around 6 carbons?
14.
14. So you're going to take the max minus the actual equal total divided by 2, and that's equal to degree of unsaturation. For the max, we want to know what is the maximum of hydrogens could be around 6 carbon atoms. To figure out the maximum hydrogen around 6 carbon atoms, you can do it 2 ways. If it's a small number, you can always get there and actually draw out 6 carbons in a straight line and put hydrogen atoms around it. When you start getting big numbers, you can still do the same thing by doing a little formula type one. You can actually, even if you can't remember the formula one on small atoms, you can always just draw it out. For the bigger ones, you really kind of stuck it for bigger atoms. You really got to go ahead and actually use the degree of unsaturation formula. But most atoms we're dealing with are going to be less than 10 or so. So you probably what you really can do when you get stuck in a pinch is to draw them out and then put the number of hydrogen atoms around them. But for this molecule, what is the maximum hydrogen atom that can be around 6 carbons? 14. Minus, what's the actual hydrogen atoms we have in our molecule? 6. 14 minus 6 will give us 8. 8 is our total. We're going to do what our total? Divided by 2. And that would give us 4 degrees of unsaturation. Yes.
So the 14 came from plugging in the seats with the, remember that 14 the max?
Yeah, I'm just trying to figure out what the maximum hydrogen is going to be around 6 carbon atoms.
Saturation.
Yes. So basically, saturate tell me what the maximum I can come up with. This is the max. No hydrogen around 6 carbon atoms.
You did say saturation.
I'm going to then look at my actual. Take this number divided by 2, and that will give you 4 degrees of saturation. Yes. I know you're probably thinking. Jasmine is thinking, but what if I had a molecule that has like bromine, chlorine, and stuff in the molecule? What if a molecule had like oxygen or sulfur in the molecule? What if my molecule had like nitrogen or phosphorus in the compound? How would you treat that? I'm like, Jeff, I wasn't thinking about doing something like that. But Jasmine asked that question, and there's a rule to address it. Let's have the molecule C7H3, Br2, F2, N2, O3, P, S. My numbers work out right. 8. Yep. 7. 7, 5. You know, no, we have to make sure it wasn't an odd number because it turns out we can't do it. It doesn't work with an odd number. And actually, we can't get the degree of unsaturation for this molecule right here. Now we got our handy dandy periodic table. Again, there's a rule about how to handle different type elements in the periodic table. Everything in the molecule got reduced down to just 2 atoms, carbon and hydrogen. I got to take all those elements and reduce them down to just carbon and hydrogen. So we're going to talk about how to end up handling different type groups. How to treat group 7A elements. in determining the degree of unsaturation how to handle group 7A. Anybody know what the name of the group 7A on the periodic table? The halogens. How to handle the halogens. On group 7A, treat them as if they were hydrogens. They are hydrogens. In our formula right here, this molecule right here, which atoms belong to group 7A? Bromine and fluorine. So if we're going, I'm going to break these figures if they were hydrogens. I'm going to redo this particular formula one by converting all my group 7 elements, bromine, fluorine, could be chlorine or iodine, either one of those. I'm going to convert those into hydrogens. So I'm going to do my formula again in which I converted all my bromines and fluorines into hydrogens. This makes my formula C7H7 N2O3PS.
Okay.
The next one for the periodic table is going to be group 6A. Treat them as if they were class clowns. Treat them as if they were class clowns. They are class clowns. And how you put a treat class clowns? Ignore them. Ignore them. So we can then do, what about group 7 elements? I mean group 6 elements. Oxygen and sulfur. So we can rewrite that whole equation and just ignore oxygen and sulfur as far as degree of unsaturation. So that now becomes C7H7 N2P. Oh, yes.
It looks like, so we could be, okay, the first part, the group 7A, we are treating like hydrogen.
So basically, when we, in this right here, there's these Br2 and F2. We converted that to hydrogens. There's still 3 hydrogens.
Oh, okay.
We then made these 4 groups into additional hydrogens to give a total of 7 hydrogens. Eventually, in doing the degree of unsaturation, everything got to reduce down to just carbon and hydrogen. Can't have any other element besides carbon and hydrogen. The last one, how do you treat that group 5A? For every 5A element removed, remove a hydrogen. How many group 5 elements do we have?
3.
And nitrogen,
And phosphorus. we're going to lose 3. 2 N's, 1 P. For every one N I'm losing, for every we lost total of 3, I also lose a total of 3 from my hydrogen. So it's going to reduce down to being C7H4. Yeah. This molecule reduces down to be C7H4. What we've just did is just come up with our actual structure. We have not come with the degree of saturation yet, we just came with the actual structure. We took that same formula and reduced it down to just carbon and hydrogen by following particular rules. Now you got the molecule down to the actual. We use our formula to find the degree of saturation. What is the maximum hydrogen for 7 carbon atoms? 16. The maximum is 16. Minus, what's the actual? 4. That would be a total of 12. Divided by 2, give you 6 degrees of saturation.
Can you tell me how you got H4 again? I know we have to remove a hydrogen for each element removed.
For each group 5 element.
Okay.
On the periodic table, what elements are group 5? This is how before we ever removing anything. Those are group 5 elements. And phosphorus. How many total elements from group 5 do we have? Total. I'm trying to trick you. From here, from the thing. How many total? 3. There's 2 nitrogens, right? And 1 phosphorus, total 3. I'm not trying to trick you, but I want everybody to see that there's 3 of them, right? 2 atoms of nitrogen and 1 atom of phosphorus. So I'm going to lose 3 of those. When I lose 3, for every one I lose, I also have to lose a hydrogen. So when I lose 3 hydrogen atoms, I'll come down to just 4 hydrogens. Isn't that funny? Hold up. Hold up. Jamie. Jamie is asking the question, what is that telling me? All I said was like 5 degrees or 4 degrees or some number right here. But what is that telling me about the molecule?
They can form more bonds.
It would figure what it telling me. It would actually tell you that we have either double bond, single bond, a double bond, triple bond, or a ring in a molecule by doing the degree of unsaturation. What does in the degree of unsaturation tell us? All we're going to do is a simple addition type things. All we're going to do is use different combinations to make up higher numbers. We're going to have a 1 degree. 1 degree is equal to 1 ring. 1 degree is also equal to 1 double bond. You're only going to have 3 different combinations to deal with. A ring, a double bond, and there's a 2 degree one, which is a triple bond. Now for a 2 degree, you also get a triple bond. What's another way to get a 2 degree? All we do is take those numbers we got so far and just add them together. Give me a way to make a 2 degree.
2 double bonds.
2 double bonds. Let me try to move it over here for some spot here too. You also get a 2 degree by 2 double bonds. Each double bond is 1 degree. 1 times 2 is 2. Give me another way to get a 2 degree. 2 rings. Give me another way to give me a 2 degree. 1 ring, 1 double bond. Now we did when we had like 4 degrees on saturation. Give me a combination to give me 4 degrees on saturation. And the 4 degrees on saturation, these are the numbers you have to use. These are the values you use in order to make them higher numbers. Give me ways in which, give me 5 ways to give me 4 degrees on saturation.
2 triple 1.
4 degrees of unsaturation. What we start with?
2 triple bonds.
Even easier than 2 triple bonds.
4 rings.
4 rings. Let's get a pattern to it. We have 4 rings. We can have 4 double bonds. Now you want to use a triple bond, you can use 2 triple bonds. Instead of doing 4 rings, you can do what? 3 rings and a 3 rings. Now I'm going to get number 3 is already 3. 3 plus what give me 4? 3 rings and a double. 3 rings plus 1 double. Or I can do 3 what?
3 doubles.
3 doubles and 1 ring. So I come up with, what is 5? We get 6 ways.
You can do 2 rings and 2 double bonds.
We can do 2 rings plus 2 double bonds. So they give you 2, 4, 6. You also give me 1 triple, 1 ring, 1 double. Triple will be 2, ring is 1, another double bond is another 1. They give you a total of 4. But notice all we're doing is just basically adding the little small numbers up together, different combinations of just 3 numbers, 1, 1, and 2. The triple bond is the only one to get a value of 2. Like 1, 1, 2, just give different combinations as far as the molecule. Then we get the molecule, which is 4 degrees, C6H12. C6H6. A combination of C6H6 would be 3 double bonds and 1 ring. C6H6. Medium one C6H6. We got 4 degrees. One of the combinations you could use would be 3 double bonds and 1 ring. 1, 2, 3. This molecule has 6 carbon atoms, 3 double bonds, 1 ring. Do we have 6 hydrogen atoms attached to the molecule? How many bonds the carbon 1 to 4? Start with the top. How many bonds to show? 3. I need to add a what? 1 hydrogen. 1 hydrogen. 1 hydrogen. 1 hydrogen. 1 hydrogen. 1 hydrogen. Now again, what it does, it doesn't say what molecule you can actually use, it just tells what kind of combination you come up with. You also can do a molecule, similar molecule, if I give you 2 triple bonds. So I'm not forming a ring, I'm going to do 6 carbons in a straight line. 1, 2, 3, 4, 5, 6. Where you want to put your triple bond at? You can please, once you can put it in the same carbon atom. But you can put it any place you want. I can put a triple bond here. I can put a triple bond there. Now remember that molecule, we should have a total of, what's my time?
Time for a
We
break.
didn't take a break yet.
It's time for a break.
Yeah,
no, it's
asking about a couple minutes, we can just finish the day and stuff.
Yeah.
Do that.
Pretty much.
So rather than finish up to a number, by the time you take a break and get back, it's time to leave.
Time to go.
Let me do the number for the big. Now, when we said for the number right, if we do it right, we should have 6 carbon atoms, and it should only be, if we have 6 carbon atoms with 3 double bonds, I should only have 6 hydrogen attached to it. Let's see what type of trip, are you making it feel or not? We're gonna look at the first carbon atom. How many bonds is shown? 3. So we're gonna add a what? 1 hydrogen. Yep. Look at the next carbon atom, how many bonds shown?
He's already got 4.
Do we add a hydrogen? No. Look at the next carbon atom, how many bonds show? 2. We need to add 2 hydrogens. Next carbon atom.
2.
2 hydrogens. Next carbon atom.
No.
See, the 4 bonds with no hydrogen, right?
Yeah.
And this we add 1 hydrogen. That molecule has 6 carbon atoms, 6 hydrogens, and it also has 2 double bonds. Again, what the group saturation does, it doesn't tell you, like, it doesn't say that it has to be this molecule or that molecule. It tells you possible combinations you can use in order to get that molecule. Yes.
This will be an exam, right?
No.
It's going to be on the next one?
We'll put the next one. We're going to do the exam here because we just kind of nearly got started right here, and I'm not sure how comfortable I'm trying to feel about for us doing that one, and we can still always do it on exam numero dos. Now we will have the name of the molecule we did earlier by the name of the cyclohexane and the Jordan molecule, and it may also have for us the little different instructions for the formula type things. But not at this, but none of the derivative saturation stuff.
What about the isomers?
Isomers, we get one question, 2 questions about how to do the isomers, but not a whole bunch of things. I don't want to get like a feel about doing the isomers. Good question. How do you do that? 2, 3, 1, 2, 3, 6. You cannot even get 3 rings in one double out of that one. It turns out you can't even get a, that's 2 rings, 3 rings in one double. From the structure point here, you cannot get 3 rings and stuff out of the molecule. You can do a 7 3, 3. 1, 2, 3, 4. 1, 2, 3. And double. 1, 2, 3, 4, 5. It'll look like something like this right here. Would it happen for this molecule? You probably could say even make a process to actually make the molecule. It's not going to be it's not going to be stable. It's not going to be able to form that particular molecule. The problem with this molecule right here, in case you want to look, if we even draw the molecule stuff like this right here, it has a whole bunch of big problems. The little bond angle inside the molecule already got a 3-membered ring, which is going to be very strained. And then on top of that strain, you can put another bond angle. The bond angle requirements for the molecules, sp, sp2, sp3, gets all crazy with a particular molecule. You can probably end up being on paper drawing a particular molecule. You can never probably form that molecule. Some of these molecules start coming to, we start getting like really crazy stuff. You're like, nah, that can't work that particular way. But that'll be one if I have 3. That actually have 3 rings. 1 ring, 2 rings, 3 rings. 3 rings. You got 1, 2, 3, 4, 5, 6 carbon atoms. And do the number we actually have with a double bond. We actually had 6 hydrogens. You have a hydrogen here, hydrogen here, 1 here, 1, 2 here, 1, 2 there. 1, 2, 3, 4, 5.
It's more.
That's 1 here.
1, 2, 3, 4.
There's already 4.
1, 2, 3, 4. No, it would work because yes, this card doesn't have 5 bonds. Go put a double on that molecule, let's not put it some other place. Let me try to put it here.
One is 2.
No hydrogen there. And that would be a structured molecule, we have to end up getting that one. It would not get, basically there's so many big problems with that molecule, you couldn't even get that particular molecule made. Well, you can always kind of draw it, but you won't actually make the molecule. Yes?
So when you're determining degrees of saturation, you'll never have an actual hydrogen that's odd.
No, if an odd number doesn't work at odd numbers. You cannot, in part of group one saturation, you may be able to do a calculation wrong, but you never come with an odd number. It's never odd number.
The actual.
The actual molecule never be an odd number. Now, you can actually have a molecule before you do the structure called an odd number. But the reason why the odd number, you have a nitrogen atom attached to the molecule. If I do C3H2, NH2, how many total hydrogen atoms will be shown in the molecule? You have 1 carbon with 5 hydrogen and nitrogen. If I want to determine the degree of unsaturation for the molecule, when I give it a nitrogen atom, I will give it an extra hydrogen atom. The reason why you gotta do it for the group 5 one, because group 5 forms 3 bonds. Because of forming the extra bond and stuff here to get the degree of unsaturation to work, you have to subtract out the extra hydrogen atom. And that way you eliminate the process of being an odd number. If you didn't do that one, then you would end up, if I just ignore it or just move the nitrogen atom, I would end up having carbon atom with more than, if it's an odd number, also carbon, I'll be saying carbon actually has 5 bonds. And carbon doesn't have 5 bonds. As far as exam numero uno goes, no degree of unsaturation stuff on that one. Because again, just send me some more questions of the degree of unsaturation. And I don't want to just go pound it on you right now. At the last minute, you still have some questions about that. So no degree of unsaturation. We'll have naming, drawing, and give a couple of different structures of the same molecular formula. Now remember, if I give you something to do with the molecular formula ones, I will give you, for example, like I did earlier, C7H14. I would ask you for like 5 structures, but I knew it could be more than 5. I'm not gonna have what you got to get there and keep on forever to try to come with the structures of the molecule. So one thing we have like drawings, no degree of unsaturation on exam 1. The degree of unsaturation, we put it off until exam 2. So let's give you a chance to ask a question about it after the class. After the exam on Monday. Monday we'll have our exam. The first thing we're going to do is actually take our exam first. Then after that we'll start in the lecture part of it. So don't come here 30 minutes late for the exam, because we complete. As we finish the exam, we have an hour. We then have a 10-minute break, and after 10-minute break we then start class. So you really would actually have 70 minutes to complete